Hello, everyone, and welcome to today's webinar, Utilizing Stationary Phase Design in Method Development, which is part 2 of a 3-part series titled A Systematic UHPLC and HPLC Method Development Strategy with Complementary Stationary Phases to Maximize Selectivity and Resolution. My name is Alex Nase from MacMod Analytical, and I will be moderating today's webinar. If you have any questions during the presentation, please type them into the chat and include your name and company. We will try to answer as many as possible in the Q&A portion at the end. If you miss anything or would like to review the content, we will send a recording of the webinar as well as the slides to everyone via email. You will also find a collection of our past webinars and resources on MacMod's website. MacMod is a chromatography company that offers scientists innovative solutions for their complex separation needs. We recommend and supply the best columns and accessories to our customers. We also provide application notes, technical notes, white papers, and other up-to-date resources from industry-leading scientists to keep you informed. Today's speaker is Gemma Lowe. Gemma is a global portfolio manager at Avantor based in the UK, responsible for the self-manufactured chromatography portfolio, which includes HPLC, UHPLC, GC, TLC, and sample preparation columns from workflow solvents. Gemma has over a decade of experience working in the HiChrome technical support team, troubleshooting chromatography methods, recommending sustainable column chemistries, and supporting the vast range of chromatography columns. Additional experience in HPLC column manufacture and business development are used to support the portfolio. Originally a biochemist, focus areas include the analysis of biomolecules and polar analytes by various chromatographic techniques and working in close collaboration with the Avantor R&D and application teams. Thank you for joining us today, Gemma.
Thank you, Alex, for that lovely introduction, and thank you everyone for joining me today to understand where stationary phases fit into our selectivity and method development processes. So we're going to think about how our stationary phase design can support different method development approaches and understand a bit more about the column chemistry and how sensible or really schematic phase design has been used to introduce functionality to enhance selectivity through different mechanisms of interaction. So I want to first thank MacMod for inviting me to present. We've been working together for a very long time, and it's always a pleasure to get an invitation like this to talk about our chromatography offerings. So I'm going to start with C18 columns because C18 is the most commonly used phase that we've got in reverse phase chromatography. And that's generally because it works. A lot of the time, our complex mixture of analytes will be run on a C18 chemistry column, and we get a separation, or we work really hard to try and get a separation. We've generally always got a C18 column in the drawer from one vendor or another. And in terms of what we'll get from those columns is a hydrophobic mechanism of interaction. So our hydrophobic analytes are retained on a hydrophobic stationary phase. Now, not all C18 columns are exactly the same, but in terms of their retention mechanism, they're all utilizing hydrophobicity. So you've got a long alkyl chain that is the only mechanism, or should be, if you've got a high purity stationary phase, that should be the only mechanism that can interact with your analytes. So I've got an example here where we've got 16 analyte mix, and you can see, if I can get a pointer, you can see that the analytes on every C18 phase elute 1 through 16, 1 through 16, 1 through 16. There's slight differences in the retention time, in the K value, in the selectivity, but there's not a significant difference. You're not seeing a big shift in the elution order of the peaks. So C18 columns are not all the same, because you can see there is different retention times, but in terms of the mechanism of interaction and really the power of a C18 phase, they are all going to be quite similar. And you can modify the mobile phase, you can modify the temperature, you can modify the gradient steepness, etc., to get separation on the majority of these vendor stationary phases. So they're all similar in terms of their selectivity. And you will see that when you go to different length stationary phases. So for example, if we start with the C8 stationary phase, so it's got a shorter alkyl chain than the C18, that has elution order 1 through 5. That's going to be the same elution order as your C18 column, 1 through 5. You see differences in the amount of retention you're getting. So you've got more hydrophobicity on a C18, therefore more retention. And the same goes for a shorter alkyl chain, short C4 chain. Now I've got elution order exactly the same, 1 through 5, but the retention times are different. They're shorter. There's less hydrophobic retention. But I'm not really changing. I'm not really influencing cell activity. If you want to start moving your peaks around, you need to look at additional stationary phases. For example, something like a cyano phase or a phenol phase. Now you've got 3-1-5-4-2 or 1-3-2-4-5. So the elution orders are significantly different from our starting point. So when you're considering which columns to have in your method development kit, do think about different mechanisms of interaction, different types of stationary phase, because they're going to give you a wider selectivity space to be exploring. So as I mentioned, C4, C8, C18, main mechanism of interaction there is hydrophobicity. When you're thinking about cyano phase, it's a strong dipole. When you're looking at a phenol phase, it's more of a pi-pi interaction with the analytes in your sample. And you can really start from your analyte structure and think about how is that going to interact with my stationary phase. You can see here an example of an alkyl chain, C8 chain. It's got those hydrophobic interactions with your hydrophobic analytes. But when you start introducing more alternative stationary phases, you get different interactions, so pi-pi interactions. If you've got a polar embedded group, this can have some hydrogen bonding. The AFP phase is very interesting because you've got both pi-pi interactions, you can have some hydrogen bonding, and potentially you can have some hydrophobicity in there too. Here's your strong cyano phase with that strong dipole on the end. And if you've just got a bare silica, or maybe you're working with an older generation type A silica, even with a C18 bonding, you might start to see some additional interactions that come from the silanols on the silica surface. So when we're considering our method development, we need to think about all of those potential chemical interactions. How is my analyte going to retain? Does it have polar groups that could interact with the dipole? Does it have aromatic groups that could give us more pi-pi interactions? There's lots of potential chemical interactions that we've got available to help retain compounds. That's what we really want to do. We want an interaction of our column with our compound to give us retention. And the more different interactions we have available, the more opportunity we've got to change the selectivity. So if you go back to kind of basics, how we're manufacturing these columns, you start, or predominantly, most of us have silica-based columns. So within, or on top of a silica particle, you have these residual silanols. And these are fantastic because it's what we bond to when we want to add that C18 chain. But also the different types have different pKa values, or they give the silica a different pKa value. And what I mean by that is they can be potentially more acidic or less acidic depending on the type of silanols that reside on the silica surface. So as column manufacturers over the years, we've tried to push the silanols on the surface more to associated forms, which are least acidic, because then you don't get secondary interactions. You should just get the interaction of the ligand, that C18, rather than anything coming from the surface. But if you're using some of the older generation columns, maybe you're getting some silanol activity. If you start to see those tails on your peaks, there's more things than just the hydrophobic interaction going on, and it might be coming from some of these base silanols. We do try and cover them up as well as push them into that less acidic form. So here, for example, we're talking about end capped columns. So we've taken that original silica surface, we've bonded on our C18, and then we've added in an end capping reagent, something like TMS, to cover up more of the surface silanols and stop any additional secondary interactions. But you can still see there's going to be free silanols on the surface. So we have to try and push those into a less acidic form so that you've got good peak shape, especially when you're looking at basic molecules. But as I've mentioned, C18 gives you hydrophobic interaction. It just gives you that one mechanism. And if it's not enough and you're not seeing a good separation, and especially when you want to go to method development, it's good to choose a column that's different. And that phenol ring is something that really works nicely in method development. So when we were designing our stationary phases, we kind of started there and said, well, this is really good. I can have pi-pi interactions. I can have an electron rich ring that can interact with aromatic moieties on our analytes. So we'll proceed with that and develop more of a phenol column. We thought the same for the pentafluorophenol, so PFP. Interestingly, it has the opposite kind of electron status. So this is a deficient ring, whereas we have the rich ring from the phenol group, and therefore they're complementary selectivity. They're not going to give you the same retention, the same elution order for your analyte mix. So they're quite nice columns to have for your method development. The problem with these types of stationary phases historically was always that they were less hydrophobic. So your retention times for your hydrophobic analytes were always shorter. And also that can lead to a less stable phase. So potentially you get some phase bleed. You see the baseline start to creep up because you've got some stationary phase falling off. So what we did was we combined the alkyl, long alkyl chain, plus the phenol ring, and the same again for the pentafluorophenol. And that gave us best of both worlds, really. You managed to get more stability for the phase, so less bleed, especially if you're doing mass spec studies. But also you got those additional mechanisms of interaction, so more selectivity, higher alpha values. It also gave the advantage that they're 100% wettable, so you can use them in 100% water because it's a more polar stationary phase than our, hydrophobic fatty C18. And really what happened when we developed these was the chromatography showed both mechanisms. And here's just an example of that. You can see this 9 analyte mix. On a C18 column, I've got coelution of peaks 2 and 4, horrible coelution of peaks 2 and 4, but generally everything else is separated baseline. On a phenol column, you can see peaks 2 and 4 have a nice separation. But now I've got coelution of peaks 9 and 8. And if you combine both mechanisms, hydrophobicity plus pi, you get a good separation of every analyte in that mix in this case. I'm not saying the C18 is a bad column, I'm just saying it's the wrong choice for this application. And again, with the phenol, it's not a bad column. You've got much less retention because it's less hydrophobic. And therefore, if you're trying to compare columns, that may skew the data a bit. But combining both moieties, both phenol and C18, you get a good separation in this case of all of these NSAIDs. And exactly the same story for the pentafluorophenol. So with the PFP, we looked at a mixture of methoxybenzene isomers. And here on the C18, the hydrophobic marker looks great, but these 7 analytes just coelute. It's very poor chromatography, and it's going to be a real challenge to try and develop that method on that column and get baseline resolution of all 7 of those peaks. Pentafluorophenol does brilliantly, separates these out, gives you much clearer understanding of what's in the sample. But it's a short link PFP, so instead of having a long alkyl chain, you've got something like a C3 linking it to the surface, and therefore you've got a smaller separation window. The C18 PFP pulls everything apart, including that hydrophobic marker, and you get good separation. I mean, you've got too much separation here potentially. You can go to a shorter column, smaller particle size, and really optimize this further from there. But you've got that wide separation window to play with, that big selectivity space. And as I mentioned, the PFP and the AR don't actually give you the same selectivity. They're different, and therefore they're quite complementary from each other. So you can use them, you can utilize them in method development to get alternative selectivities. I talked earlier about embedded polar groups, and having an amide group in a C18 chain or a long alkyl chain really does give significant advantages for selectivity. In addition, the cyanophase is really has significant differences in selectivity, and you can use it in normal phase as well. But it suffers the same story. If you have a short linker here, potentially it could bleed off. If you've got a longer linker, it makes it more accessible for reverse phase. It's more hydrophobic, but you've still got a strong dipole here for polar interactions. And just my favorite example of the polar embedded phase being significantly different from a C18, coelution of these 6 analytes and really poor retention under 4 minutes. If you put them down the C18 amide, you get really significant improvement in selectivity, in resolution, and in retention. So that polar embedded type phase is a good alternative if you've got, I mean here, aromatic rings, if you've got shape differences. So these are steric isomers, you can see the difference in the OH groups, on the methyl groups, and therefore that phase gives you some nice shape selectivity as well. Another thing to play with is pH. So if you've got a pH stable phase, for example, this one here, we've got like a capping on the surface to protect it from dissolution at high pH, then you can really play with pH and get much better retention of basic molecules, and it just changes in selectivity really. So here you've got an 11 component mix at pH 3, run down a pH stable silica based column, in this case the Super C18. If you run it at pH 10.7, you can see from here it looks a bit different. If I put in the arrows, you can see significant changes in the retention of each of these analytes based on the nature of the analyte. So when you change the pH, you're changing the ionization of those analytes, and therefore if you're making them more hydrophobic, they're going to retain better. So that's good for bases, and you can kind of tell by the way the peaks move what the nature of those analytes is. If you are making them more acidic, then they're going to lose retention. So it depends on your mixture, but having that pH available to exploit really is a good tool to have in your kit as well. If you're looking at unknown samples, it's interesting to try different stationary phases. For example, I don't know how many peaks I should be finding in my sample. On a C18, I've got 4. On an AR, so that's the C18 plus the phenol, I found a 5th peak. When we put this down the PFP, we saw 7 peaks in what looked like a 4-component mixture. So the power of selectivity in finding hidden peaks, co-eluting peaks is really powerful when you've got unknown samples as well. So it's worth looking at different selectivities. And again, I've got a nice example here. This was kind of those methoxybenzene isomers in that case. But I've got another example here just showing a much more complex mix run on the C18 where we could identify 22 peaks. I mean, this one looks to me like it could be 2 peaks. Maybe there's another couple. C18 PFP found another 6 peaks hiding in there. Just really does show you the power of selectivity with those unknown samples. You should really exploit different mechanisms of interaction when you've got more complex mixtures and unknown samples. And often you'll get separation of things that were coming out in the T0 when you go to a more polar phase or a phase with different mechanisms like those pi-pi and dipole interactions. So I've only mentioned a few stationary phases, these kind of more novel chemistries that we offer. We've looked at them and we've designed them so they're different, so they can be utilized for method development. But obviously there's other phases that we haven't touched on, not just from us, but from other vendors as well. So it's worth trying different stationary phases when you're running your method development tests. We've got loads of information that can help you sort of identify selectivity, and this one I pulled out because I think it's interesting to show the science behind it that I haven't really been able to cover in much detail today. But they can all be downloaded from MacMod's resource section on their website. So please do visit that area, and there's loads of extra resources for you to look at. I believe that I've come to the end of my talk. Hopefully it's given you an insight into stationary phases and how powerful they can be when you're developing methods. And I'll pass back to Alex to ask if there's any questions in the chat. Thank you.
Thank you, Gemma, for the presentation. I don't know, I feel like selectivity is such a great topic to talk about, and I know I have quite a few questions, so hopefully the audience does as well. A reminder that you can ask questions by typing your question into the chat window, and please include your name and company. That way, if for some reason we don't get to your question, we are able to follow up with you and get you an answer. Okay. First question, are there a different number or a certain number of chemistries that you recommend when you're starting a method development project to try?
That's a really good question. We've worked with different companies over the years who have had different strategies. We tend to use 6 more because our instrument can take 6. So we've got a 6-column screen, and that's what we utilize. I know I've worked with pharmaceutical companies who've had like an initial 6-column screen, but then they've got a backup screen or whole screen, depending on the nature of the analytes. I would say 3 correctly chosen columns that have significant differences in selectivity is a really good start. And again, some of our systems in high chrome, we only have a 3-column switcher, so we do utilize 3 columns for those. But definitely, yeah, I would say a minimum of 3 would be my recommendation.
Okay. Next question. C18 is usually a starting point for a project. If the C18 doesn't work, do you have a particular selectivity that you like to try after that?
I think if you know anything about the structure of the analytes, that often guides us where to go next. So for example, if I can see there's a lot of aromatic groups on the analytes of interest, I'd probably go for something like the C18AR. That one seems to work really well for those aromatic compounds. If I knew log P values or log D values were really low, so it was much more polar, then maybe something like the embedded polar group. So the C18 amide would be the first choice. But if we don't know if you don't know anything about the nature of the analytes, I think that the C18AR is a nice second step, and it is kind of based on that phenol that we always went to historically, but with more stability and more flexibility when it comes to high aqueous, etc.
Okay. How does pH impact the chemistry of stationary phase versus chemistry of analyte?
That's a fantastic question. So I would say it depends on the column, the stationary phase, and your base material. So for example, if you're working with a silica-based column, that can have a very differing pKa based on the age of the material or the sort of generation of column that we're looking at. So older generation columns would ionize at lower pHs than the new generation type B, high purity, ultra inert type phases. So it will depend on what column you've got. But if you're going up to pH sort of 8, 9 on a silica based column, all of them are going to have an ionized surface. You're going to start seeing some of those O negative groups. So the silanols could be ionized, and therefore you might start to see some interactions potentially, depending on end capping, etc. So you could be changing the ionization on the silica surface and changing the ionization on your analytes. And then if you're working with a charge phase, again, or a, depending on if it's a wax or a sax for an ion exchange type method, again, you could be changing the ionization on the actual stationary phase ligand as well as the silica itself. So it's quite a complex, quite complex that. And therefore you do get massive differences in selectivity. I mean, when we've compared columns, we've seen bigger differences when you've got one column at 2 different pHs than sometimes, a phenol versus a C18, because it's really powerful.
Okay. Is it just the column chemistry that's important for selectivity?
No, there's lots of other factors. I think the first webinar we did touched on things like the mobile phase and, your organic modifiers, your pH, all of those factors. And if you're running gradients, then all of the column dimensions come into play as well. So there's lots of factors that affect selectivity. The column chemistry is one of the biggest ones, or is the biggest one. And when you think about how columns are made, they can have different pore sizes, they can have different pore shapes, they can have different end capping, as well as the ligand. So it's very hard to say one column is a backup column, because potentially all the columns are going to give you a slight difference in selectivity because of all the variables in the manufacturing process between different part numbers, I mean, not within the same column.
Okay, I think that's all the time we have for today. If you had a question that we did not get to, we will follow up with you via email. And just a reminder, we will send out a link to the recording and slides sometime early next week. Also, if you found this talk helpful, please register for part 3 of this series. Part 3 is on December 12th and will introduce a screening platform for HPLC and HPLC method development. We will include links to register in the follow-up email, along with links to watch the recording of part 1 in case you missed it. Thanks again to everyone for joining today. Thank you, Gemma, for a wonderful presentation, and have a great rest of your day.